All right, in this video, we're going to talk about electrochemistry in more detail, how to determine the voltage from a series of redox reactions that have occurred. So for now, we want to get started by just a little bit of review, see if you can remember how to determine who is the oxidizing agent in here. You can always pause the video because I'm going to go kind of fast through it. Remember, step one is to figure out what are the oxidation states of each of the elements, and then you can decide who is the oxidizing agent. And I'm going to pause. All right, hopefully you picked, in this case, B, the dichromate ion. How do you know this? Well, if you go through and assign the oxidation states, you're going to see who is reducing in its oxidation state, and you'll notice that chromium starts as a +6 as a reactant, going to a +3 in the product side. So when we're choosing the agent, we're choosing the element that is reducing, and the agent, we pick the whole compound. Or in this case, the only thing that was listed for chromium was the ion. All right, so we're going to get ready here to learn about cell potentials, the voltages that we can use to calculate ahead of time when we're trying to build a battery or determine an electrochemical cell, or just determine if two things are going to react and transfer an electron. So we're going to see how this table is set up, this information is used, and how we can relate it back to other useful ideas like spontaneity, Gibbs free energy, and eventually equilibrium at some point. All right, so a very important tool that we've been learning about is the reduction potentials. These are the half reactions that we use to help assess whether a reaction is going to go or not. This is a very helpful tool here that we should get familiar with. But our first job is to learn, where did this all come from? How did scientists figure out what are these voltages that go along with each of these half reactions right here? This was all done based on establishing a reference. And that reference is the standard hydrogen electrode, sometimes SHE, S-H-E, standard hydrogen electrode. That electrode is composed of hydrogen gas and having a bunch of hydrogen ions around. So when this electrode is partnered with another chemical reaction, we can then determine the half reaction potential, or the voltage that goes with that. So this is the standard reaction that goes with the reduction of hydrogen ions to produce hydrogen gas. So this reference right here is established at 0 volts. And an important definition is that a volt is a joule per coulomb. 1 volt is equal to a joule per coulomb. This starts to connect us with the energy world with the term joules. Coulomb is something new, so we're going to have to get familiar with that. That is the measure of charge. And this charge is how many amps are flowing per time, or in the amount of time that's the experiment's being measured. So the standard hydrogen electrode, we can set it up as the cathode or anode, and just depends on the chemical reaction that we're partnering with. There's platinum also involved in this experiment here. The platinum metal that's inside of the hydrogen electrode is important because it is the place where electrons can be transferred, accepted, or given off, depending on the chemical reaction. So this particular standard hydrogen electrode has been partnered with a zinc metal and zinc ion solution. And there's a voltmeter in between. And then the voltmeter is hooked up to the black wire in this particular example, and it gives us a positive charge. The positive charge indicates that the direction of flow here for us. The black wire is the anode here. This side is losing electrons. So zinc is losing electrons to hydrogen here. The hydrogen ions are then taking the electrons and being reduced into hydrogen gas. The voltage that is seen on this experiment is assigned to the half reaction that goes with zinc oxidizing into the zinc ion. It's important to note that the platinum metal electrode is very important because hydrogen is a gas. How do you hook that up into a solution? And so we need it there. And we also, we could use other metals or other materials. But platinum is used because it's very hard to oxidize or reduce that metal. So it's inert, we say. And so you'll often see that as a common choice there. We use metals like platinum in the experiments when you do not have a nice metal to transfer electrons in that particular half reaction. Okay, so the cathode on this side was the standard hydrogen electrode. So this reduction of hydrogen by zinc metal looks like this for the overall reaction, but we end up assigning the oxidation potential of 0.76 volts to this half reaction here. So this indicates now that zinc is actually and this is where I have my students typically click in, but you don't have to now, is a better reducing agent than hydrogen because it is being oxidized. The oxidizing element is part of the reducing agent. All right, when this half reaction, the standard hydrogen electrode, is partnered with copper metal and copper ion, we see something totally different happen. There is a plus 4 volts that happens, but this happens, positive voltage happens when the two electrodes are switched around so that the anode is on the standard hydrogen electrode and the cathode ends up being with the copper side. This indicates that copper has a different oxidation reduction potential relative to hydrogen. In fact, it is now, it wants to be reduced, the copper ions want to be reduced instead of being the metal being oxidized with zinc. So it's behaving very differently. The electrochemical cell notation is often how scientists like to denote this, and they'll put the platinum in there as part of the hydrogen side. All right, so this is why now when you partner zinc in a zinc solution with copper metal and copper solutions, the zinc is going to act as the anode and copper as the cathode because those two metals behave very differently. Zinc rather wants to oxidize and give off electrons, and copper ions have a good potential to take that. Putting these two reactions together, we can come up with an overall cell potential or voltage that this battery combination would come up with of 1.10 volts. So we need an oxidation and a reduction half reaction in order to partner to come up with this. So a convenient way, or maybe not so much to general chemistry students, convenient way is to actually organize all of these half reaction voltages into a table that is listed by the reduction potentials. So that means something even like zinc that would rather be oxidized is listed in a reduction potential. So the reaction's flipped around, and when you flip it around, we flip the sign of the voltage, and we list it as a reduction. You can see the subscripted RED there. So we flip the sign when we reverse the reaction. Okay, and then all these reduction potentials are listed in a table. That way there's some variation in order to all of the half reactions and different metals and different substances on whether they're going to be oxidized, reduced. So elements and compounds and metals and all these different things are listed here. And here's the standard hydrogen electrode right there in the middle. I think that's an important to memorize, is hydrogen ions gain electrons to make gas, gaseous hydrogen. So the elements that really like to be reduced are the best oxidizing agents, and they're listed in the upper left-hand corner. Those are the reactants there: fluorine, silver ions, cobalt, hydrogen peroxide, so on and so forth. These give the highest voltages, and these are the best oxidizing agents because they want to gain electrons and be reduced. So that means on the bottom right-hand side of the table, the elements that are in the product side actually here are going to be our best reducing reagents. Why? Because they want to be oxidized. So we'll actually have to think about those in reverse. So because the way that they're written right now, those metal ions produce the negative voltage. That is unlikely. Why? We're going to have to see the connection between voltage and free energy, and we will in just a few minutes. So this table is an important one to understand, so I leave it here for you to see it in all its glory. Now, we can ask questions now like, which metal is the strongest reducing agent, which means it wants to be oxidized, and thus would provide the greatest potential voltage when it's oxidized? Which one of these metals? Well, I would jump back to this table here, and go, which one wants to be oxidized and give off the greatest voltage? Well, hopefully you can see now that element is lithium. Lithium was the one that was here in the bottom right-hand corner, and lithium metal, when you think of that reaction and it's reversed, will produce a 3 volts. Now you can understand why there are a lot of lithium batteries, because it gives off a lot of voltage when it is being oxidized. The metal, not the ion. All right. So one way to look at these standard potentials to determine the overall cell voltage is to do what's called a distance calculation. The distance from the reaction that's acting as the reduction at the cathode minus the reduction potential from the reaction that's taking place at the anode. Now, so that means you can just go grab the numbers from the table, and you can see this distance from the upper left to the bottom right here. This can sometimes be a little bit confusing, so I'm going to show you a second way of doing it. But this is just grabbing the numbers off the table, put in who's acting as the cathode, put in the number from the reduction table there, who's acting as the anode. The negative sign serves to flip it, the reduction potential for the chemical reaction that's in the oxidation side. So if you were to partner silver ions here and copper metal, you could come up with a plus 0.46 by taking the reduction potential that's taking place at the cathode, that's going to be the silver, minusing what's happening at the anode, which would be copper oxidation, the reverse reaction. So I have two methods. This looks like there's a lot of information there. I'm going to quickly go through it. The first method we just talked about there, you figure out who's the cathode, who's the anode, and you subtract them. The second method, which I'm going to do quite a bit of here in my talks, is actually I'm going to, in my head, do the sign flip. So if I understand who is taking, what reaction and what processes is occurring at the anode, the oxidation, I'm just going to go ahead and flip it in my head or on a piece of paper, and I'm going to flip the sign. Once the sign is flipped for the voltage, the potential, the chemical reaction that you understand, you can't flip it anymore. You cannot go back to the E cathode minus E anode formula. So I just simply add them up. I like that because it's a simple thing. I flip the sign, I add them together, you should get the same answer. So there's no double flipping though, like double dipping, no double dipping, no double flipping. You can't flip the sign, plug it back into method one's equation. So once you flip the sign, you're done. Now, once we know these things, we can do some valuable investigations onto which chemical reactions are going to occur in a particular set of conditions. Let's say you had some cadmium and cadmium metals and cadmium ions and iron ions in different solutions. Could we form a voltaic cell, a battery that will generate positive voltage? If we could, what would we come up with? So I figure there's probably 4 different ways that you could come up with chemical reactions. Which one of these 4 would dominate in this particular set of chemical reactions? And how do you tell? So spend a moment and pause the video and see if you can figure out if it's A, B, C, or D. Which one's going to occur? And how can you tell for sure? All right, let's see what you picked. Here's how I went through the thinking to figure out which chemical reaction to decide that's going to occur or not. So I actually eliminated A and D. Why? Because you're not going to have 2 metals react in this particular regard here, because the way that the chemical reaction is written, it shows that both the elements are oxidizing. So we can't have 2 things that are oxidizing. D shows 2 ions that are being reduced. Can't have that happening either. We need to have something oxidizing and reducing. That's B and C. So one of these is going to work. How do we know? Let's analyze B. So when I look at B, I see that cadmium is a product going to cadmium plus 2. That means it's oxidizing. So I go look up the reduction potential for the cadmium ions, and I flip it around so it matches my chemical reaction right here. So that gives me an oxidation potential of 0.4. Now iron plus 2 is being reduced, and I can just grab its reduction potential from the table, and it's negative 0.44 volts. So I'm going to add the oxidation and the reduction potentials together, and I get a negative 0.04 volts. Oof, not a whole lot, and it's negative. So we're going to see that this is actually a non-spontaneous chemical reaction. This is less likely to go. Now, like when I look at C, I see that cadmium plus 2 ions are being reduced. So I'm going to go grab that reduction potential for cadmium ions and just use it as here, negative 0.4. Now, iron now has flipped from where it was before in B, so iron's being oxidized into iron plus 2. So I go look up its reduction potential for the iron plus 2 ion, and then I flip it around, because this is the way the chemical reaction is intending to go here, or at least that's the way it's written. Now I'm going to add the oxidation and reduction potentials together, and I get a plus 0.04 volts. This thing is greater than 0, and it's more positive than the other one. So this is the reaction that's actually that's going to work. So C is the one that's going to work. And notice the analysis process that I have to go through to figure that out. So C is the answer here. So if I were to hook these two things up, I wouldn't expect a whole lot of voltage, but I do see that iron is a better reducing agent than cadmium, and the cadmium plus 2 ions are a better oxidizing agent than the iron plus 2. So this combination of iron metal and cadmium plus 2 ions are the ones that are going to really drive this chemical reaction to take place. And so I'm showing the other way to do this. Once you've figured out who's the cathode and who's the anode, the cathode being the thing that's being reduced, which is the copper ions, the cadmium ions, and then the oxidation from the iron metal. And then I can also figure out it's plus 0.04 volts. So these standard potentials are very important for us to predict which chemical reactions are going to go. Well, how do we know that the positive 0.04 volts is worth anything? I mean, what does that mean? Well, this is, we need an important idea here to connect this. I want to just mention one of the early scientists, Michael Faraday, from 1691 to 1767. He actually did a lot of work in this electrochemistry field, gave us the terms anode, cathode, anion, cation, electrode. He helped discover electrolysis and a lot of magnetic properties of materials, and then the combination of electricity and magnetism. Now, chemists that day did a lot of different areas. He also got involved in synthesizing and understanding other materials like benzene. And he went around giving lectures and demonstrations. I feel akin to this guy, not only because he was a lecturer, but he's also a Christian. All right, so his name's going to come up here in a little bit. So how does this cell voltage connect to thermodynamics? There is a simple mathematical relationship between the cell voltage and Gibbs free energy. It's proportional to the number of electrons that are being transferred and this voltage here. And the reaction, or I'm sorry, the chemical mathematical expression that relates these two thermodynamic ideas is that the Gibbs free energy is equal to minus n, the number of electrons being transferred, times this F, which is a Faraday's constant, times the cell voltage. Faraday's constant is 9.6485 times 10 to the 4th joules per volt per mole of electron. Sometimes also written as coulombs per mole per electrons. This has to do with the definition of what a coulomb is, which I gave earlier in the talk. So N is the number of electrons transferred, which you figure out from balancing the redox reaction. We learned how to balance redox reactions in an earlier lecture. You might need to go back to that to review. So if I take the reaction between copper and silver here, and I see that I can get a positive voltage if I oxidize copper metal and I reduce silver ions. So my oxidation potential plus the reduction potential here gives me a total of 0.46, a positive voltage. Now, when I balance these two chemical reactions, I need to have two electrons that are given off with the copper, and 2 electrons in the balanced chemical reaction are used by the silver ions. So they have to have the same number of electrons, and that's what we come up with when we balance them. That too is very important, because we're going to use that 2 electrons that are being transferred in this Gibbs free energy equivalency here to the cell potential. So 2 moles of electrons go in. That'll cancel out with the moles of electrons in Faraday's constant, leaving me with joules per volt of 96,485 joules per volt. Now the cell potential 0.46 is plugged into this equation and the volts cancel out and I'm left with just joules. And in fact, negative joules. I can divide by 1,000 to get into kilojoules, and I see that I have a Gibbs free energy of a negative 89 kilojoules per mole. And so now we know that, going back, we know that Gibbs free energy of a negative is a spontaneous product favored chemical reaction. So from this equation, we can make then the connection between the signs of Gibbs free energy. So when it's negative, then that is dealing with a spontaneous and product favored chemical reaction. And now we see that when we have cell voltages that are positive, this means a spontaneous chemical reaction is taking place. The opposite is true. When Gibbs free energy is positive, we'll have a negative cell voltage. We want to make these connections here. All right, so that's it for now. A lot to chew over, to go practice and see if we can learn how to predict whether electrochemical reactions are spontaneous or not. Thanks for joining me. I'm Dr. Ryan Hayes at Andrews University, and proud to be a member of the Chemistry and Biochemistry Department. Hopefully you've learned a few things about electrochemistry in this talk.